Good morning. Thanks. Yeah, this is a small class today, it looks like, so the onus is going to be on you to ask some questions and interject when I ask you questions. As Dr. Wasser mentioned, my name is Megan Cattau. I'm a postdoc, just a research associate at the Earth Lab, where Dr. Wasser is the education director. So I'm going to give you, I understand she's talked with you quite a bit about passive remote sensing. So I'm going to give you just a very brief overview of some of the general concepts of that, touch on some of the products or processes to evaluate fire using passive remote sensing, and then jump right into some case studies. And I want you guys to feel free to interrupt me at any point. So you can raise your hand or just yell out. Is anyone in Carol Westman's landscape ecology course? Okay, so you've not already seen these. That's great news. Okay. So again, we're going to just talk about evaluating fire processes from satellite data, a review of some of the theory surrounding passive remote sensing, some commonly used products or methods to evaluate fire, and then we're going to jump into some case studies. These case studies are all going to be surrounding fire in the peatlands in Indonesia. So I'll just give you some background on what fire processes are like in peatlands, because it's quite different than in most other areas, because the fire can actually burn the soil. It goes subsurface, and that's pretty unique. We're definitely going to get to a case study on modeling fire probability, almost for sure a case study on mapping fire ignitions. We most likely will not get to this last one. It just depends on how many questions you guys have, and that's totally fine. When we talk about each of these case studies, I'm going to talk with you about the data, how I've processed it, also some of the methods, conclusions, and results, but I want you to think about how some of these data or how some of the methods I used could be useful for you in your own work, either in this class, in your final project, or going forward after you are done with this class. So first, just briefly, this is generally how passive remote sensing works. Energy, solar radiation comes from the sun. It goes down to the Earth's surface. Before it hits the Earth's surface, what does it have to go through? The atmosphere. Goes through the atmosphere, interacts with elements on the Earth's surface, goes back through the atmosphere, and then is measured by the satellite, in the case of satellite remote sensing. I do want to note that remote sensing is not always detected from satellites. It can be from a variety of platforms. Airborne, drone-collected data, that's all remote sensing. If someone has, let's say this is a plant, let's say someone has a sensor and they're measuring something right next to a plant. Is that remote sensing, do you think? Yeah, you can't do it when it's cloudy outside, that's true. But
That'd be remote sensing.
that's a good point. Remote sensing is anything at a distance. There's no specification on what that distance is. So if you have some handheld instrument and it's right next to a plant and you're not making direct contact with that plant, technically that's still remote sensing. You're sensing it remotely. But what most people mean when they're talking about remote sensing are sensors mounted on satellites, drones, airplanes, that sort of thing. The visible part of the electromagnetic spectrum is a very small part of the spectrum. So all visible light just falls in this part of the spectrum. So one main advantage of remote sensing is that you can gather information that you couldn't with the remote sensors that are embedded in your face, that you can't see with your eyes. Any questions so far? I want you guys to feel free to interject. Okay. Light interacts with elements on the Earth. It comes in as incident radiation, it's transmitted, it's absorbed, or it's reflected. A green plant reflects what colors? Green, yeah. Green plant reflects green. That's why it looks green to us, because it's reflecting all of that green light. Do you know what other types of the spectrum plants reflect? Near infrared, exactly. So if we could see near infrared, plants would look near infrared because they reflect much more of that light, even more than they do green light. They absorb a lot of blue and red. That's the wavelengths they use for photosynthesis. So you can think of plants as sort of eating blue and red light. They use it to create their energy. Every object has a reflectance spectra. Is this something you all have seen before in this class? You have, you've seen it. Okay. Okay, it's a familiar concept, so I'll just touch on it briefly instead of going into extreme detail. But each of these lines of different colors are different elements. So clear water, turbid water, vegetation, etc. If you look at the percent reflectance over the different wavelengths, you can see that each of these elements has a pretty characteristic reflectance spectra. And there's some variation in this that's not accounted for in this figure, of course. So this is just one, piece of the spectra. This is green vegetation, something I think is quite interesting. What do you think this little peak is here? Just to give you a hint, this is in the visible part of the spectrum for green vegetation. Green. Exactly. So this is a little green blip in the spectra. This is near infrared. So you can see how much more near infrared light plants are actually reflecting relative to green. Another thing that's kind of interesting is that this red line is dry vegetation. So in this case, you can see between dry vegetation and green vegetation, it looks pretty similar in the green part of the spectrum, but it's quite different in the near infrared part of the spectrum. So that's one kind of common thing that people that do vegetation studies can see. If there's some sort of compromised plant health, if it's dry, for example, you can see that much more quickly in the near infrared part of the spectrum, and often much more dramatically than you can in the green part of the spectrum. Great. So this is how a commonly used sensor, the thematic mapper that's mounted on the satellite called Landsat, that's how the bands of that sensor map onto the electromagnetic spectrum. So these are various bands. There's also a band number 6 that's in the far part of the spectrum that's not depicted here, but these are 6 of the 7 bands. So for each of these parts of the spectrum, you'd get 1 value per pixel when you download that satellite data from Landsat. So it's covering a part of the blue, green, red, near infrared, etc. So this is a commonly used satellite. So something that is interesting to note is that when people are designing these satellites or the sensors that go on these satellites, they're deciding what part of the spectrum they want those bands to cover. And what do you think are some considerations for where the bands map onto the electromagnetic spectrum? That question make sense? Yeah, sure, absolutely. When people are designing these sensors, they're deciding where on the spectrum to place the bands, where they want to measure on the spectrum. What might they consider? What are some factors that might go into that decision? Yep. Yep. So for example, these are 2 elements, right? In the red part of the spectrum, they're not very easily distinguished. In the blue part of the spectrum, you can see they're quite easily distinguished. So one consideration might be placing those bands in locations where you could easily distinguish different elements of interest for that sensor. Okay, so the way that this works is that you very often will get a DN value. So if it's an 8-bit value, is this something you've discussed yet? Okay, so when you download satellite data, you're often getting, for each pixel, you'll get something called a DN value. And if it's an 8-bit, it ranges from 0 to 255. And that has to be converted into percent reflectance. I won't go into too much detail about this. And part of it is that you can currently download a lot of data that's already been converted into percent reflectance, whereas a couple of years ago, you had to run algorithms on it to correct for atmospheric interference. So that's one positive thing about some recent developments in this. But I want to note here that this is an example of actual reflectance spectra for some element, for green vegetation. Because you're only getting 1 value per pixel when you download data, the spectra actually gets simplified to look like this, right? You can't see any variation within that band. So the width of the spectrum that band covers, you're getting 1 value per pixel. Any questions about that at all? Digital number. Yeah. Okay, I'm not going to get too much into active remote sensing today. Just one slide to note that it exists, and it's pretty cool. So where passive remote sensing, where does the energy that the sensor is detecting come from? The sun, exactly. In active remote sensing, that energy is actually sent out from the instrument itself. And the time it takes for that energy to return to the instrument is what's measured. So it's energy from the actual instrument rather than energy from the sun. What are some common applications of active remote sensing that you may have heard of already? Sonar, yeah. Right, big hint there, there's a graphic of it. But you might have this kind of instrument on your ship to detect the sea floor or to detect fish even. People will use it often above forests to map biomass or to map canopy structure. Okay, so that's the brief overview of what you all have covered in class so far. I'm gonna shift now to talk about fire processes. Isn't this awesome? So this is a global map of fire distribution as detected by the satellite MODIS, or the sensors mounted on the satellite MODIS. This is scrolling through every month over a variety of years, and you can see these patterns of fire flashing in and out. The role of fire on Earth is changing. I mean, since the mid-1900s, and even more so toward the end of that century, fires have become more frequent, larger, more intense in many parts of the world, and this is especially true in the tropics. It's particularly relevant in the tropics because most or a lot of those systems haven't evolved with a fire regime, and so they're much more sensitive, ecologically sensitive to changes in fire regimes, to increased fire. Currently, fires in the tropics are bigger and more frequent or more intense than other areas of the world, which is a novel situation here. Yeah. Yeah, absolutely. Yeah, so many parts of the world are driven by wet season, dry season dynamics in terms of fire regimes, so that's why you see that cyclical pattern. You're seeing a lot of fire during the dry season, and this is not true in all parts of the world, of course, but in many parts of the tropics, that's what you see, an extreme dry season fire regime, and then it scales back during the wet season.
America, I got focused on Africa.
Yeah, in North, so here I can go back, but it's so, I think it's kind of interesting, in the US especially. Oh, it's now refusing to work. It says no. Here we go. What we're seeing in North America is there used to be a much narrower, this is the US actually, a much narrower temporal window in which fires occurred, but we're having increased anthropogenic or human-caused ignitions, which is expanding the fire season into those shoulder seasons by about 3 months. So the temporal pattern of fire is changing as well as the characteristics of fire itself, like severity or size. Okay, so I want to tell you about some of the most commonly used available options for evaluating fire processes from spectral remotely sensed data or from passive remotely sensed data. The first is active detections, and these are what, for the case studies I show you later, this is what I've used, is active detections. Both MODIS and AVHRR satellites provide near daily data. And fires are detected based on an algorithm that uses the thermal bands of those data. So the thermal band is measuring heat. So there's an algorithm that basically detects any pixel in which there was a measurement over a certain threshold in the thermal band. This product designates that pixel as having experienced fire during that date. Both of these products are freely available online, which is wonderful, and they can be downloaded relatively easily. AVHRR is only considered reliable over forested areas, so that's one advantage of MODIS over AVHRR. So these products give you the point location of the pixel in which a fire occurred, but not the size of the fire or where in that pixel that fire is located if it's a sub-pixel size. Does that make sense? So we could have this tiny fire in this pixel, for example. It's going to show up as the centroid or center point of that pixel as flagged as having had fire in that pixel. As another example, you could have 2 small fires, but the actual product you get is identical, right? It's just saying, yeah, there was fire in this pixel. Alternatively, you could have a huge fire, a large contiguous fire that covers multiple pixels, and again, it's just gonna flag individual pixels as having had experienced fire on that date. So if you have multiple pixels that have a positive flag. You don't know if that's spatially disaggregated small fires or one large contiguous fire, which is one of the complications of using these data. And in the second case study, I'll go into some workarounds for that. Okay, instead of detecting a fire from the heat coming off the fire as it's actively burning, you can also evaluate the area on the ground that has burned after the fire has already occurred, and this is burned area products. You can derive these yourself, but there are a variety of pre-processed products already available that you can download. Burned area is usually characterized in these algorithms that were used to develop the pre-processed products by charcoal and ash, removal of vegetation, or alteration of the vegetation structure. So a very commonly used one is the MODIS burned area, and that comes at a 500 meter square resolution, and it's near daily. And you can download that as a monthly product. So for each month, the first date that pixel burned in that month is what the data look like. The advantage of these is that they're pre-processed, they're relatively easy to use, but the disadvantage is that typically they're relatively spatially and temporally coarse. So 500 meters might be a fine spatial resolution for you, just depending on what your questions are. Multi-year data is often not available, but it's becoming increasingly available. Another way that you can look at fire on the ground is just doing band composites for visualization. Have you all discussed band composites yet? A little bit? Okay. So remember, what you can do is you can load different bands that represents different part of the spectrum into different color guns to visualize that data differently. So a really commonly used band visualization that you may have already done is loading the near infrared into the red color gun so the vegetation looks red. Did you guys do that? Okay. Yep. Yep. So this is a commonly used composite to detect fire scars. And this is for the Landsat TM sensor. It's a 742 composite. So this is a fire, and you can see pretty clearly where that fire scar is using that composite. And again, this is just for visualization. This is not quantitative. It just gives you a way to sort of look at the landscape, evaluate what's going on before you do any quantitative processing. And then finally, you can actually do math on individual rasters that you get by computing indices. Did you guys do the NDVI index? So again, that's an index for vegetation. This is an index for fire. So an NBR index. This is taking the near infrared minus the shortwave infrared divided by the near infrared plus the shortwave infrared. You typically will do an index from a pre-fire scene and a post-fire scene and then subtract them, and then classify that result so that you can get categories of fire severity. So in this example, they've categorized it into high, moderate, low fire severity, and then unburned area. And with all these things, I just want to note that having ground validation data is really important. I mean, you can compute indices, you can do a band composite, you can use the active fire products, but unless you have some way of validating that on the ground, you're not positive that it's correct, right? So it's important, if possible, to even go into Google Earth and extract some points in which to validate your products here. So I'm just going to briefly summarize these fire products. Again, pre-processed products that are available, MODIS burned area, for example. Band composites are one way of visualizing them, and then indices you can compute. Any questions about any of those products or common ways of evaluating fire?
Resolution from MODIS, which is a kilometer square resolution from the previous slide.
Yeah, I'd have to follow up on that, but I'm pretty sure with the kilometer square, it's upscaled. So some of the MODIS products that are available are 250 meter, some are 500, and some are... I'm not familiar with the mechanism of that, but yeah, there are a variety of different spatial scales. If anyone has the answer and wants to answer that.
The answer 250.
There you go.
Chunk or 500 meter, and then I think there are some kilometer. I haven't worked with the stuff further out, but I'm assuming they just have different gratings or something on the instrument that's fractionating it at various scales. I'm
Yeah,
not sure exactly
that
how.
makes total sense.
Yeah.
So I assume if you're using the bands that have that 250 meter resolution, the final product can have that resolution, but if you're using the other bands, you can't have that finer scale.
It's good enough for me.
Yeah.
Cool.
Okay, we're gonna jump right into the case studies then. So this is all about forming questions and case studies. How do you pair remotely sensed data with ground-based data? And I've picked some projects that use different amounts of remotely sensed versus on-the-ground data. The first is about fire probability, and this uses almost exclusively remotely sensed data. The second, which we'll probably get to, also uses almost exclusively remotely sensed data. And this one uses a combination of remotely sensed and other data products. And again, I'm going to talk with you about the data, how I've processed it, and also the conclusions, but I want you to really think about the data sources and how they've been processed and how that might be useful for you moving forward. So I mentioned the changing role of fire on Earth in general, particularly in the tropics. And I just wanted to note that fire in tropical peatlands are following pan-tropical trends. They're getting larger, more frequent, more extreme, or more severe in recent years. And again, this is particularly true mid-19th century, even more so, 1900s, sorry, even more so toward the end of that century, and is continuing to increase. So peat is characterized by its soil. Peatlands are characterized by peat soil, which is really carbon rich. So who's heard of peat soil before? So everyone, okay. Are most of you familiar with it in temperate regions like Ireland and Scotland? Yeah. So if you've heard of peat soil in Ireland, you know people will dig it up to actually use as fuel. And it burns less frequently there than it does in the tropics because it's colder and wetter. So when you have this kind of peat in the tropics, it's more susceptible to burning. So what peat is, it's partially decayed vegetation matter. It's been accumulating for thousands of years. So you can think of it as a precursor to coal. It's really carbon rich. Typically, it's inundated fairly close to the surface with water for most of the year, so it's not very likely to burn. But like any fuel, when it becomes dry, it's more likely to burn, and this is the case in peatlands as well. Most tropical peatland can be found in Indonesia. This is a distribution map of peatland within Indonesia. And that's all I want to say about that for the moment. The fires in these peatlands compromise the variety of ecosystem services that are provided by those peatlands. Fires can cause peat subsidence, which results in flooding problems downstream. It can cause saltwater intrusion. It causes loss of habitat for a variety of endemic flora and fauna. There's elevated human mortality, which is mostly a result of health consequences from particulate matter emission. And then there are high economic costs, and those are associated not with just direct suppression efforts, but also missed work days, lost timber and crop resources, the health impacts, et cetera. And then probably the most commonly discussed consequence is carbon emissions. So above ground biomass burns, trees, vegetation, that sort of thing, and this is the case in most systems where there's fire. But again, something that's really unique about this system is that most of the carbon loss comes from burning of below ground biomass, so from the peat soil itself actually burning. And there are estimates that the carbon in peatlands, so a 10-meter deep peatland, has about 12 to 19 times the carbon as other tropical forest systems. So it's a lot of carbon. And why do we care about carbon? Why do we care about carbon emissions? You all know this, I know you do. Greenhouse gases, Anyone want to expound upon that?
With increased carbon, it's trapping more radiation within the Earth's atmosphere, warming the planet, melting sea ice.
Exactly. Yeah, so it can contribute pretty substantially to global warming. And it takes this pool of carbon that normally would be under the ground as sequestered carbon and releases it back into the atmosphere. So in 2015, Indonesia had one of the most devastating fire crises that it's ever had, and this is just a smattering of headlines that followed that fire crisis. With this increased international attention came a desire to better understand these fires, the causes of these fires, both sort of the proximate and ultimate causes. So I'm going to take you to an area of lowland tropical peat swamp forest in central Kalimantan, Indonesia. So this is, people often call this Borneo. This is the island of Borneo. Malaysia owns the top part. Indonesia owns the bottom part here. It's divided into 4 provinces. This is the province of central Kalimantan. So within central Kalimantan, there's this area. This is about 1.5 million hectares of lowland peat swamp forest. This is the Sabangau National Forest. It's a protected national forest. It's pretty intact. It's a large swath of forest that hasn't had much degradation. It's had some small-scale logging, but it's a pretty nice primary forest. And this is a failed agricultural project called the Former Mega Rice Project. This project was developed in the mid-90s by the Indonesian government with the goal of converting this 1.5 million hectares of lowland peat swamp forest into rice paddy. The project failed and it was abandoned, but only after pretty considerable environmental damage had already been done. So they cleared a lot of the forest outright, and then they put these canals in, and here's a graphic of these canals. These are intended to flood the area, again, for wet rice cultivation, but the way that the hydrology works in the peat meant that these canals actually drained the water out of the peat. So it dropped the groundwater level, leaving the peat pretty dry. And why might that relate to fire in peatlands? Easier to light on fire, yeah. When it's wet peat, it's not going to be an available fuel source. And as soon as it dries out, it becomes a fire-susceptible vegetation source or biomass source. Sorry, let me just scroll through that. Okay. So most of the fires happen in the dry season. So this is month of the year. This is the number of fire detections. You can see that the vast majority of them are happening in this dry season. So 98% of them are happening July through November. And there's almost no fire in the wet season. From 2000 to 2010, about 41% of the area burned at least once. And this is an area that historically has not had much fire, if any at all. So almost half of this area has experienced at least one fire since the development of this project. This is showing you the interaction with groundwater levels and canals. So it's a little confusing. You can imagine this is the surface, the soil surface. And then this is a canal right here. This is distance away from that canal, rivers on either side. So you can see groundwater depths are lowest close to that canal, which is, I think, kind of counterintuitive. I mean, you see a canal, you can see the water. I would imagine that the soil would be more wet close to that canal, but that's not the case. As you get closer to that canal, the soil is actually drier. And again, that's because it's draining the peat from that canal. Does that make sense? Okay. This is showing you what the landscape now looks like. So there is a mature, or like a forest fragment in the background here. And those forest fragments are surrounded by degraded land that's dominated by ferns and bushland. So you can see this is an area that has previously burned. This is an area that is not burned. To give you a visual of these canals, you've seen this picture, but this is, you can imagine yourself inside of the canal looking at the side, and you can see this peat profile here. So that's what the peat soil itself looks like. You can see that they've used heavy machinery to dredge that peat in order to create the canals. And I don't know if you can see, there's a cute little old couple in a canoe inside this canal, just for scale. So they're pretty big. You can take a canoe inside of these canals, many of them. This is a visual of what the landscape looks like. Again, you've seen this picture, but there are patchy remnant forest fragments that are surrounded by this degraded land. This is a fern that dominates much of the area after a fire passes through. This is just a little burn scar that you can see how that landscape looks after it's burned. This is a view from an observation tower. So imagine yourself about 40 meters up on top of this tower, and you can see pretty clearly a line of where the mature forest starts and where this degraded matrix begins. I would guess that this area burned about 15 years ago, and you can see there are some trees growing back. Can you guys see the difference in that? Yeah, much more open, smaller trees, but still relatively green, not totally barren, which is encouraging, I think. Yeah.
Peat soil though?
It is. It's all peat soil. Mm-hmm. Yeah. I'm going to just real quick actually go back to that distribution map of peatlands. So the red is peatland area. And the area we're looking at is right here on top of that peat dome. So that whole area is and always has been peat. But the majority of Indonesia is not necessarily peatland, it's mineral soil. Okay, so going back, there are people that live on this landscape, and they'll get in these small motorized canoes and take them in the canals to access different areas. And usually what happens is they'll go from these riverside villages. I want to show you. So these riverside villages that are pretty small, they're up on stilts, and they'll take their canoes into degraded areas or into intact areas to collect songbirds, to hunt for bushmeat, and to fish. And they're going to use fire during some of these activities. So they'll use fire, for example, to gain access to fishing ponds during the dry season drawdown. There are also accidental fires from escaped campfires or from cigarettes that aren't extinguished properly. And there's a lot of recreational arson, which is true in the US as well. Just teenage, mostly in this case, it's very frequently teenage boys just lighting fires for something to do. People will also use fire next to their small holdings. So this is, again, a little village along the river. They'll use it to burn trash, and they'll use it to clear an area to plant agriculture. And sometimes fires from those activities will escape beyond their control. There's illegal logging in the area as well. And people will use fire to gain access to trees as they're conducting this logging. And then the final kind of land management activity I want to mention to you is that there's oil palm cultivation. Who's heard of oil palm? Most people at this point. So oil palm can be grown in peatland, and a lot of edible oils cannot be grown in peatland, which is why you see a lot of oil palm in peatland. To make the soil dry enough for that oil palm to grow, people will put canals in so that it's sufficiently dry. People also use fire on these concessions, so they'll use it to clear the land prior to the initial planting, or after harvesting one cycle, they'll use fire again to clear the brush out to plant again. Also, there is a fire used as a result of land tenure disputes between local people and oil palm concessions. Okay, so first case study is about peatland restoration and how and if it can mitigate the impacts of climate on fires. So we're going to ask, what are the relative effects of climate, human access, vegetation, hydrology, and fire history itself on the probability of fire occurrence? And I'll talk to you in a little bit more detail about why we would care about each of those factors. And then second, what's the potential for peatland restoration to offset the impacts of climate on fire? So there's evidence that all those aforementioned factors affect fire probability or fire occurrence, but the relative contribution of each of those factors hadn't been comprehensively evaluated. So climate is the biggest factor driving fire disturbance in most of the tropics, and most people think fires in Indonesia are also a result of ENSO-driven droughts. So this is a figure from the study area that I showed you, from that former mega rice project. What this is showing you, this is a climate index called the Niño-4. It's measuring sea surface temperature anomalies and giving some indication of atmospheric dryness. So it's basically a measure of how dry is the climate over time. So again, this is over time. So the higher this line, the drier it is. This line is showing you what would be considered an El Niño phase or an extremely dry phase. So anytime this line goes above that red dotted line, it's an El Niño phase. Anytime it goes below, it's an extremely wet phase. These gray bars is the number of fire detections. So you can see there's this coupling between when there's an extremely dry phase, there are often a lot of fires occurring at the same time. This is showing you something similar. This was generated by a group called IRI. This top portion is showing you vegetation. So anytime it goes below the 0 line here, it's a low amount of precipitation. Did I say it was showing you vegetation? I meant to say it's showing you precipitation. So there's not a lot of rain happening. And again, this is just the number of fires. So you can again see this coupling between really dry periods and fire occurrence. Okay, so other people think that these fires are a result of positive or amplifying feedbacks that are perhaps totally decoupled from climate. So feedbacks between fire history itself, changes in vegetation, and hydrologic alteration, which may or may not have a relationship with climate. And then finally, the way that humans access this landscape is going to affect fire probability just because of increased ignitions or increased human-started fires on this landscape. So you often see elevated ignitions close to infrastructural elements, like roads, or in this case, perhaps close to those irrigation canals because people are using them for transport. So we developed a Bayesian model to estimate the probability of fire occurrence. And this is as a function of variables related to climate, fire history, hydrology, human access, and vegetation. And I'll break down what those individual variables are. I first want to talk about how we generated the response variable. So for each month, we have a binary burned, unburned raster. So remember we talked about the MODIS active fire data. I know that you just learned this, but who can recount to me what the MODIS active fire product looks like? What data do you actually get? And it's okay if no one remembers. Oh wait, you look like you remember.
Is that what you're asking for?
No, not quite. So I will remind you guys, let me try to use this thing. So this was the product that has, I'm terrible at drawing, sorry, but I'm just going to give you two scenarios. So these are two individual pixels. And remember, if you had a fire anywhere in this pixel, it gives you just the center point of that pixel. It just flags it as like, hey, there's been a fire here somewhere. So remember, a product that looks like this could be one large contiguous fire. It's a fire. Or it could be multiple small fires. And you're not sure which it is. So that's one disadvantage of using these data, but that's what we did because it has near daily measurements. So we created a burned, unburned raster from this product for every month. So let's say this is, again, a bunch of pixels. Let's say this one burned, these ones burned on the 1st of the month, this burned on the 5th, this on the 15th, and this on the 22nd. So what we would do is we'd create a raster that basically says, in this month, these pixels burned. Oops. And these ones didn't, right?
If it's any present.
Fire that it won't flag it.
Yeah, good point. So this one is just using the thermal band. So what this one is doing is it's saying as the fire is actively burning, if there's enough heat coming off from that pixel, it flags it as a fire. But the burned area products, there are a lot of studies about different burned area products in different areas and how big the size of that burn scar needs to be for it actually to be flagged. And those burned area products are usually looking at the characteristics of that landscape before and after a fire. This is just looking at when the fire is actively burning and the heat coming off of that fire. I did see a study, and I can't recall the numbers, but the size that the fire typically was in order to be first detected in this landscape, and it was relatively small. I can't remember what the size was, but it was picking up things, sometimes even like campfires. Quite small or can be quite large. Yeah.
Or kind of like false detections from industry or like human-made, I don't know, activity that have flagged?
Yeah, I mean, you can often have false positives for fire. In this landscape, it wouldn't be from human activity so much as sometimes a really dry, barren area might get flagged as fire because the soil itself is actually hot enough that it's registering as fire. And in this landscape, that might not be a positive, it might be a true positive because, again, there can be those subsurface fires. So it might actually be heat from a fire below the ground. The commission error, I think, is 60%, I want to say, sometimes in this landscape. I could find a paper for you and give it to you if you're interested. Yeah. So that was the response variable. These are the predictor variables. So for climate, we have the sea surface temperature anomaly. So remember that figure that had the Niña-4 index? That's the information that was used to derive this climate variable. Variables related to hydrology are distance away from the irrigation canal, distance away from the nearest river, and then we have interactions between hydrology and human access. Why might we include interactions between those two things in a model? How are people using those irrigation canals? They're using them to dry the peat soil out. And then additionally, there might be increased human-caused ignitions, right, close to those canals. So if you see more fire close to a canal, it could be the hydrology. It could be because the groundwater is actually lower. But it also could be because people have better access to that area, so they're actually lighting fires more frequently. Does that make sense? Cool. So human access are distance from cities and roads and rivers, from populated places. And then we have information related to vegetation. So there's a MODIS-derived product called vegetation continuous fields, which for each pixel gives you the % woody vegetation in that pixel. And that's something you can just download online. And that's what we used here, the % woody vegetation in each pixel. So these variables are all computed for each pixel for every month over the time period. This is a graphic representation of the model. Is anyone a math major or really into math in here? No, I will not go into detail about this then. Just, I want to note it's a generalized linear model, which allows for non-normal distribution of the response variable. All this is saying, just to break it down for you, is that we have our predictor variables related to climate, human access, vegetation, hydrology, fire history, which I just showed you. Those feed into our response variable, our predictor. So what's fire risk? What is fire probability as a function of those variables? Just as a note, we have some process error, so it just allows for some stochasticity in process, and then some observation error, because no observation is perfect, whether it's from a human or from a satellite. And these are just our parameter. Ah! Okay, sorry, I don't know why. Okay, great. Okay, so this is a figure showing the results of the model projected back into geographic space. So areas that are bright red have a higher fire probability. Areas that are a little softer have a lower fire probability. These brown polygons are oil palm concession areas, just to note that to you. What are some trends that you see, just some general trends? There's no wrong answer here at all. Yeah, absolutely. So you see these canals here, and you can see some linear patterns related to the canals. Maybe someone that hasn't talked yet, just throw out the first thing that you notice. I'm not looking for anything in particular, so there's no wrong answer whatsoever.
A lot of fire in the south.
A lot of fire in the south, absolutely. Yep. And you can't see that on this figure, but there is a lot of bushland and fernland in this area, and that's probably why there's so much fire down there. Great. So I also want to note that fire probability is a lot higher in El Nino phases, or dry phases, than it is in La Nina, or wet phases.
Did you figure out which one are canals? Like, did you actually use some other kind of remote sensing
Yeah.
data?
So these data are from the Indonesian government. So they have a shapefile that you can download from their government website. And then I went in and just hand digitized on some satellite data to see if it seemed pretty accurate. And there weren't any large canals that I could see that were not included. And there weren't any canals included that I couldn't see. So it looked pretty accurate. Yeah. Good question. So these are the results of the model. This is not as complicated as it looks, I promise. So everything to the right of the zero line has a positive relationship with fire. Everything to the left of the zero line has a negative relationship to fire. The variables are standardized, so the magnitude of this number tells you how important that variable is for model contribution. So basically, the bigger the number, the more important that information is in predicting fire. So what we see, the biggest number, or the variable that's most important, is climate, and that makes sense. So what this is telling you, it's a positive relationship, it's a big number. So the drier the climate, the more likely fire is, and that's pretty intuitive. Also important are the distance from irrigation canals And this is a negative relationship. So what that's telling you is the closer you are to the irrigation canals, the higher the fire risk. And I'm going to show you these relationships in a minute with a little more detail. The amount of woody vegetation on the landscape is also pretty important, this is saying. Perhaps more important than distance away from canal, but not as important as climate. This is a negative relationship. So what does that tell you? Anyone know? Lower. Yep, exactly. Yeah, so that's kind of, I mean, to me that seems a little counterintuitive because you think if there's a lot of vegetation, there's fuel to burn. But what this is telling us is that when there's not a lot of vegetation, there's a higher risk of fire. And something I just want to note is that the quadratic term is also significant. So what that means, just to break that down, and I'm going to break it down simply, but if the relationship were linear, for example, this is fire, this is vegetation. If the relationship were linear, this would say fire probability is lowest in the lowest amount of vegetation and just increases. But the relationship is quadratic, and I'll show you what that looks like with the actual data in a second. I just want you to keep that in your mind. So here it is. Oh, question? Yeah. It can be bushland also. So this is that pre-processed MODIS product called vegetation continuous fields. So for each pixel, it tells you the percent woody vegetation, percent herbaceous vegetation, and percent barren. So things that are categorized as woody vegetation could also be things that are in addition to trees, like bushes or shrubs. So this is percent woody vegetation. This is predicted fire occurrence. So you can see the highest fire probability happens around 25% vegetation. And this could be sparse trees, it could be bush, it could be barren. And basically that's because when you're way down here, there's not enough above ground vegetation to burn. As you increase in vegetation, that vegetation can catch fire, perhaps allow that fire to go subsurface and burn the peat itself. And as you increase in vegetation, the area starts to look more like forest. And forest is less likely to burn. Any ideas about why that would be? Yep. So the microclimatic conditions within a forest in this system and in a lot of systems are generally less conducive to fire. They're wetter, they're a little bit cooler, and so they're less likely to burn than like either a degraded forest or a bushland area. This is a similar graph. This is just breaking it out into wet and dry phases. So this is the relationship again between vegetation and fire during a dry phase and during a wet phase. So you can see when it's wet, it almost doesn't matter how much vegetation there is. It's a low fire probability. It's not going to burn. When it's dry, how much vegetation there is starts to matter a lot, right? And fire risk increases a lot relative to the wet phase. This is the relationship between fire probability and distance away from the canals. Fire probability, again, is really high when you're close to the canal and then drops off exponentially. Why is that? We've talked about it a little.
The closer you are to the canal, the drier the peat is around it.
Exactly, yeah. So groundwater levels are lower close to those canals. This is showing that in dry and wet phases. So again, when it's wet, almost doesn't matter where you are in the landscape. When it's dry, that relationship becomes much more important. Okay, this is the part that's really interesting to me. So this is fire probability without any restoration efforts. This is fire probability under 5 different restoration scenarios. This is replanting the area so that it looks more similar to forest. This is some hydrologic restoration, full hydrologic restoration, and then replanting paired with partial hydrologic restoration, replanting paired with full hydrologic restoration. So this is the most kind of effort-intensive one. But you can see the distance between this dotted line and the top of the histogram tells you the percent fire reduction as a result of that restoration intervention. So you can see this one reduces fire quite a bit. So it reduces fire by about 60%, which is really encouraging, I think. So in conclusion for this, Climate coupled with human alteration of hydrology and changes in vegetation affect fire probability on this landscape. And that's PSF as peat swamp forest landscape. Climate's the dominant factor that's consistent with many other parts of the tropics, so climate is the main thing driving fire. The influences of canals and vegetation are nearly as important as climate, and that was really surprising to us. Normally, any kind of factors on the ground, the importance of them pales in comparison to climate, but here they were quite important. The negative side of that is that we're still seeing some long-term impacts of that failed agricultural development, even decades after its abandonment. But the positive side of that is that changing the situation here is going to result in a lot of fire probability reduction. So if we can actually dam those canals, and if we can replant, then fire probability is going to be reduced pretty substantially. So some restoration efforts have already been implemented on this landscape, but they're pretty small scale and pretty underfunded. So these are the canals. This is just a small dam that is intended to block that water. This was actually built by a couple of 12-year-olds who were just interested in restoring their landscape, which I think is awesome. This is a slightly more sophisticated dam, and this you can see is a even more sophisticated dam. The canal runs this way. This is some wood, and they've packed it with peat in order to start stopping that water flow. After that crisis in 2015, the Indonesian government established a peatland restoration agency. They're putting some pretty concerted effort into actually restoring peatland areas in order to reduce fire. And this method that we're using here could be used to target areas for restoration. So showing which areas actually have the most reduction in fire probability as a result of that restoration. Okay, before we move on, any questions at all about that? About the data, about the modeling component, about the system, anything? Nothing? Okay. Got a little time still. Okay, so, okay, good. So I'm going to talk about a second case study about the sources of anthropogenic fire ignitions on this landscape. So where are these ignitions coming from? So at the most basic level, fire regimes are dictated by ignition source, meteorological conditions, and sufficient fuel. And those can all interact with each other and feed back into smaller scale factors. So disentangling these factors is pretty complex because there are a variety of relevant social and ecological factors that go into that. So when we think about the anthropogenic or human-caused influence on fire regimes, we can think about the factors that predispose the landscape to burning, right? So anthropogenic climate change means the landscape is much more likely to burn. But we can also think about the direct human impact, so ignition sources. How are people starting fires on this landscape? And this project focuses on just the ignition sources. Before large-scale land use change, where do you think most of the ignitions in the tropics came from? How were fires started in the tropics over historical time? Just any ideas? Lightning, exactly. So people estimate that about 90% of fires in the tropics were lightning caused historically. And now they estimate about 90% of the ignitions in the tropics are human caused instead of lightning caused. So the way that we're starting fires on these landscapes is totally changing the fire situation.
Percent was
People.
Oh, people still.
Yeah, just a smaller percent.
I was thinking, this is before even anybody was there.
Oh, no. In Indonesia, the ignitions are primarily anthropogenic as well. And who's responsible for those is pretty highly contested, both within the Indonesian government, within local communities, within the Southeast Asia regional conversation. Most land is cleared in Indonesia through the use of fire. So why would you, if fire is dangerous, why would you use fire instead of some heavy machinery? Faster and cheaper, right. So you might not have access to a big tractor. You might be part of an indigenous community that doesn't have heavy machinery. You might live hundreds of miles from a road, right? So you're not going to get machinery in there. You're going to use fire. It's faster, it's cheaper. And again, most land is cleared in Indonesia through fire. And this includes smallholders, so small villages that have plots that they're using to feed their families or their community. This also includes large-scale agro-industrial companies that have big, for example. So there's some evidence that high-impact fires often originate on plantations or logging concessions or large land clearing projects instead of smallholder projects. So there's some information that says most of the problem, quote unquote, problem fires are from these larger activities rather than smallholder activities. But it's pretty unclear. And the land tenure situation is complicated there. As I mentioned before, people will often use fire in land tenure disputes between oil palm concessions and small companies. So if a small community is unhappy with the way in which an oil palm company has come in and seized land rights, they'll sometimes use fire as retribution and vice versa. Okay, here are just a few headlines, again from 2015. These are all blaming the oil palm industry for the fire crisis in Indonesia. Some people, much fewer number of people, are saying that it's not the oil palm companies or these large projects, but instead it's small-scale farmers. So these two competing ideas about who it might be or what it might be. So with this work, we wanted to understand the origin of fires on this peat swamp landscape, and we wanted to assess this oft-asserted claim that escape fires from oil palm concessions and or from smallholder farms near settlements are the primary sources of fire on this landscape. So where are they coming from? We ask, in which land use land cover classes do fires, especially the high impact ones, originate, and where do they spread? And then second, what proportion of fires, especially the high impact ones, actually escape from these areas into surrounding land use land cover classes? And again, stop me if you have any questions. So I'm going to talk first about the data. We use, again, those MODIS active fire detections. So someone remind me what those data are. What band do they use, or what part of the spectrum do they use to detect the fires with this product? Thermal band, yeah, heat. Tell me more about this product. What do the data look like? What's it giving you?
Centroids.
Yep, centroids. So it's giving you a center point of any pixel that's had fire during that period. We derived a land use land cover class from two different sources. One, we've already talked about, sorry, I'm going to start with the second instead of the first, but it's this MODIS vegetation continuous fields product. So again, that's percent woody vegetation per pixel. And we validated this. We went in the field with a GPS and we looked around us and said, is this woody vegetation or not? Mark a GPS point. And we found that for this area, this product is over 95% accurate. So it's a pretty good product for our use here. The second thing we wanted to know is where are the oil palm concessions? So you can get the actual shapefiles of oil palm concessions from the Ministry of Forestry through the Global Forest Watch portal. And this is an amazing resource, you guys. So if you just go to Global Forest Watch, I can't remember if it's .com, .org, but Global Forest Watch, there are a variety of data sources available globally. So oil palm concessions, percent forest cover, all different kinds of data that you can use. That would probably be great for this class and then for any other projects you're doing.
It's based on Landsat data, yeah?
This one's not.
No.
The oil palm concessions are based on permits that were applied to.
Global Forest Watch data set?
The Global Forest Watch is just a portal of all different kinds of data sets.
All based, okay.
Yeah, but there definitely are Landsat-derived products in there. So there's, I think, a percent tree cover, global percent tree cover that I believe is Landsat-derived. So there are a variety of products that are 30-meter resolution because they're Landsat-derived in there. And finally, we wanted to know the village locations. So we went around this area and found them, basically. We talked with community members, asked where they knew other people lived, and did sort of snowball sampling in that way. Okay, so remember that I'm interested in the ignition of the fire itself. And again, you don't know if there's a centroid flagged as having had fire, and one in an adjacent pixel. You don't know, remember, if that's one large contiguous fire or if that's multiple disaggregated fires, which makes determining the ignition difficult, right? If it's one large contiguous fire, one of those pixels is going to be the ignition pixel. If it's disaggregated smaller fires, they're both going to be the ignition pixel. Does that make sense? So the first thing we did was to group those fire detections into actual fire events using two different techniques. One of which, the single pixel technique, did not allow fire to spread outside of its pixel, and this is kind of a conservative approach. This is the neighborhood pixel technique. This did allow fire to spread outside of its pixel. So we used a variety of temporal thresholds and said, if there's a detection in the adjacent pixel within this temporal threshold, call that thing the same fire. And we don't actually know which one of these is true. We did some validation with Landsat DNVR, but again, that doesn't have a temporal signature on it. So again, you don't know if that burned area is two fires that happen to overlap, or if it's one big fire. And so we looked at the trends in the questions we were answering using both of these products. So that you can get, this is called a sensitivity analysis, basically. How sensitive are my results to the embedded methods? So we then identified, again, from these groups, the earliest ignition or the earliest detection, because each active fire detection has a date associated with it, so you could actually pick out which of those centroid points you're given is the earliest detection within that cluster. And then we separated out the high impact fires. So we took the top 10% of fire duration, so the number of days that fire burned, the top 10% of those across the whole landscape, and heat. So fire radiative power is the amount of heat that's coming off the fire. And this is one of the things that the Modus Active Fire product gives you. For each flag, yes, this was a fire, it tells you how hot that fire was. Okay, so we calculated the percentage of fire detections and ignitions that are located on each of those land use land cover classes. This is an example of what that looks like. So these little yellow dots are all of the fire detections that were grouped into a single fire using that neighborhood pixel technique of clustering that I talked with you about. And I want to note that's hierarchical clustering. The ones that are flagged in red are the ignition detections. So then you can look at what land use land cover class did that fire start on and where did it spread. This is an example of a fire that started in non-forest. That's what this lighter green is. It spread into forest. It spread into an oil palm concession. This is kind of an interesting example. This is a fire that had multiple ignitions along the boundary of an oil palm concession and a non-forested area. It spread both further out into that non-forested area and it spread further into the concession. This could be an oil palm concession trying to expand its boundary little by little without having to get additional permits. This could be smallholders doing smallholder activities right next to that oil palm concession. This could be land tenure disputes. It's hard to know exactly what's going on, but something kind of cool. So we aggregated all those fires together and we looked at trends. So we wanted to know where do these fires start and where do they spread. So this is the land use land cover class on which the fire started. So the height of that bar is telling you how many fires started on that land cover class. So most of them started on non-forest. The color tells you where it spread to. So you can see most of the fires stayed within the land cover class that they started on, right? So these started on non-forest, most of them stayed within non-forest. Some of them spread to forest and oil palm. These are for the high impact fires, the ones that burn the longest and that burn the hottest. And you see a really similar trend. Most of those started in non-forest. Most of those stay within the land cover class that they started on. And just to go bit by bit to show, fires ignited in non-forest have the biggest impact on the landscape. Most of them are started there. And this is about 70% of all the fires. Oil palm concessions do make a pretty significant contribution. So almost 20% of them start on oil palm concessions. And this is true for all fires and for high impact fires. And then the fewest number of fires are starting in forest. Why do you guys think that is? We talked about it a little already. Oh, I saw your hand moving.
Oh, no, yeah.
Okay.
Moisture.
Moisture, yeah. So forests in these areas aren't as conducive to burning as the non-forested areas or oil palm concessions. And this is the smaller bar that I didn't mention. This is multiple. So do you remember that example of the fire that had ignitions within the oil palm concession and non-forest? That would be an example of this kind of fire. It had multiple starting places.
Could it also be that it's harder to access?
Absolutely. Yep. So a lot of times you have forested areas are far away from human settlements, from roads, and that's true in this system and in many systems. So a very trivial amount of fires started near settlements. This was super surprising to us. So the area right next to a settlement could be non-forest, it could be forest, it could be oil palm concession. This is independent of what the actual land cover class was. It's just looking at the signature of how fires are started close to those settlements. So fewer than 10% are starting near these small settlements. So what about fires that burn forest? So most fires that burn forest start in non-forest. They don't start in forest itself. Very few are starting in oil palm concessions or near settlements. So fires that are burning forest don't appear to be starting in oil palm concessions. They also don't appear to be starting near settlements. So this is another thing I wanted to note is when you think about a land use boundary, oil palm concessions, a city area, the boundary itself is somewhat artificial, right? The way that we influence the landscape is not actually a hard boundary. Instead, there's going to be some fuzzy influence as you move further away from a land use type, right? So we're interested in, as you move away from these land use types, what does the signature of ignitions look like? So this would be distance from an oil palm concession. So you can imagine an oil palm concession here, you're 0 meters away from it, you're 10 kilometers, et cetera. So you see this exponentially decreasing influence of ignitions as you move away from the oil palm concession. And this was surprising to us. This is distance away from settlements. So you don't see a decreasing trend as you move away from a settlement. Any speculation? This is, I mean, what I think it is just speculation too. So I'd love to hear what you think. Did you? Yeah, please.
Well, I have not done yet.
Oh, continue.
Yeah, but for example, people don't like to start a fire near where they live.
Exactly. That's what I think too, yeah. People don't want to start a fire right next to their village. It's dangerous. It can escape, it can burn your house, it can burn your plot. So that explains why you don't see a lot here. You see it increasing as you move away. Why do you see it drop off again? Why do you guys think?
You're too far away.
Yeah, it's just a pain to get there. It just like takes too long to get there. So this is kind of the sweet spot of it's not super dangerous, it's not right next to your village, but it also isn't a huge burden in terms of time, transportation to actually access that area. So that's what I think is happening there. So this, what we've been talking about so far is just the number of ignitions, but we have to control for the amount of land that's occupied by those different categories on the landscape. So this is the density of ignitions, how many ignitions per area. So this is the whole landscape, just 3 different views here. And these are zoom-ins of that landscape. See how they're paired? Excuse me. This is all fires. This is high impact fires. And this is just showing you the land use land cover type in those same areas. So I think it was you noted in the fire probability model that there was a lot of fire. Who was that noted there was a lot of fire down there? Was it you? Yeah. So you can see here, there's a lot of fire happening here, a lot of ignitions are happening here, and that's because there's not a lot of high woody vegetation. There's not a lot of forest there. So that's perhaps shrubland and bushland, which is burning a lot. Another example I wanted to point out was this example. You can see there's a lot of oil palm concessions right in there, and there's a high density of ignitions within that oil palm concession. So these are just some examples of what is happening on that landscape. When we break out the density of ignitions by land cover type, so remember there were very few ignitions close to the settlements, but that's probably just a function of the fact that there's not a lot of settlements there. The density is really high. So ignitions per area close to the settlements is quite high. It's really low in forests, which is not unexpected. And this was surprising. The density of ignitions in non-forest is almost equivalent to oil palm. I'm going to blitz through this. So what proportion of fires are actually escaping? So not just what fires are occurring where, but what fires are escaping beyond those boundaries into other land cover types. I just want to note that most fires that start within the oil palm concessions stay there. So most of them are not escaping into other areas. Most fires started near settlements stay near those settlements also. Those that do escape are a really small percent of all fires. So in conclusion here, we found really limited support to the claim that escaped fires from oil palm concessions and or settlements are the major contributors on the landscape. Most of these ignitions are happening in non-forest. Most forest fires are starting in non-forest, and a very low percentage of fires escaped from oil palm or from settlements. But the density of ignitions in oil palms and settlements are high, and there is a pretty strong potential for these ignitions to contribute substantially to this fire landscape if those land use types expand. So we're saying it's not currently a problem, but if these land use types expand, it definitely will be. So the solution here, I would say, is to target non-forested, degraded areas where ignitions are most likely to occur. And those are not within, but near those oil palm concession boundaries, and also outside the immediate vicinity of settlements. And I am going to not go into the third one, because I think we're almost out of time. And I just want to note that when you're thinking about using satellite data or satellite data paired with ground-based data in your projects for this class and elsewhere, first think about what are your questions? What are the questions that interest you? What spatial, temporal, and spectral resolution data do you actually need to answer those questions? Do you need data every month? Do you need it every year? Do you need it twice before and after some event, for example? Can you use remotely sensed data? Can you use ground-based data? Do you need to use both? And can you use products that are already available? I mean, there are a variety of pre-processed products available out there right now, a lot of which, again, are on that Global Forest Watch portal, data portal. If you can't use products that are already derived, can you derive them yourself? What do you need to do to be able to derive them? And then finally, are those data available and from where? And with that, I'll just take any questions, comments. Yeah.
The ground-based data hasn't validated the data?
Yeah.
Does that ever happen?
I think you'd get slammed by reviewers if you didn't have some ground-based data.
But if it always works out in the researcher's favor, I don't know. Do you know what I'm saying?
Yeah, keep talking.
Maybe we don't see those publications.
Yes, it might not
Yeah.
What do you mean, like if you have,
Publication bias.
do you mean if you have ground-based data that disagree with the analysis you've done?
Yeah.
Yeah, that means probably you need to rework the satellite-based analysis. If your ground-based data are telling you a different story, either there's some mechanism in there you haven't thought about yet, or the model you've run on the satellite data might need a little more work, that kind of thing. I mean, and sometimes you don't have ground-based data, sometimes you have other satellite products that you can use to validate the model you've run on a satellite product. And that's totally acceptable too, depending on the questions and the data. Any other questions or comments? Yeah.
Just describe a little bit more what you meant by hierarchical clustering.
Yeah. In this case, it's pretty simple. All it means is that there's temporal consideration and a spatial consideration. So, okay. I didn't go into too much detail about this, but we had a variety of temporal thresholds and a variety of spatial thresholds. So, one second to draw this thing. For example, in this example, actually, let me do one more. So I'm going to talk just briefly about the spatial thresholds first. You can create rules basically that say if two adjacent detections are within X distance from one another, those are eligible to be considered the same fire. So let's say you have to, one rule could be that it has to be within a pixel that's catty corner or directly above or below it. In that case, these would be two fires, right? You could then try again with another rule that says there can be a missing pixel in between, and that could be from misdetection. Either the fire is spreading faster than the rate at which the satellite's going to pass. So there truly have been a fire here, you just miss it because of that. So with those spatial rules, this would be one big fire. Yeah? Same thing with temporal thresholds. Let's say, for example, you give it a 3-day temporal threshold. So any fire detection that's within 3 days of the one you're thinking about is eligible to be considered a fire. Or you could say, there's some misdetections and maybe I'll allow a fire that was 6 days away to be within this one. Does that make sense?
Yeah. Sorry, could you also, did you define those rules using functions in R?
Yeah. I think the package is called HClust. So it's hierarchical clustering package.
Your generalized linear models, that was all done in R as
It's
well?
all in R. So with that,
To a raster-based data set, or?
yes. So with that one, you have your raster. You can think of a stack of rasters, and you sample each pixel. And so then you have a data frame that has basically, you can imagine it as a line or a row for each pixel. So you have your pixel ID, you have distance away from canal, you have whether there was a fire or not, you have the climate variable for that month, right?
In a stack?
Yeah. And then you put that into a generalized linear model. And I did a Bayesian implementation, which I won't go into detail about today, but sort of the beauty of a Bayesian framework for anyone that's interested in learning that kind of modeling is that you can tweak your input variables and see what effect that has on your output variable. So in this example, we said, hey, what if we change this whole landscape to look like forest? Then we can actually see how much that reduces fire probability. And in the more commonly used framework, a frequentist framework, you can't say that. You can't make those similar kind of conclusions. So that was all implemented in a coding language called Stan, for anyone that's interested in that. Any other questions?
So, do you know where the people who work on these palm oil plantations live? Do they live inside the plantation or do they live outside?
Yeah, it's so complicated. It's so interesting. They'll often live either right inside or right outside the plantation. And, it's so interesting. So I'll try not to talk too much about this, but there's a really densely populated island called Java, and that's where the capital is, Jakarta. Indonesia has this big transmigration program. Well, they'll pay people to go from Java to the less populated islands with the promise of jobs there, and usually some incentives. We'll give you land, we'll give you some money. So there's a lot of transmigrants from Java to Kalimantan that were sent there to work on those oil palm concessions. And so there are some cultural differences between the people that have transmigrated from Java and the people that are based, have always lived, and their generations before them lived in central Kalimantan. There's cultural differences between the way in which they approach fire on the landscape, which is related to your question.
Yeah. Also, the oil plantations, they're often adjacent to these open non-forested areas?
Not necessarily.
Not necessarily,
Yeah,
okay.
Yeah.
I was just curious about that too.
So is it maybe a valid observation that say maybe the Indonesian government can make that for as far as the initiation of fires, it's the best thing to prevent that is forest. But so if you can't do that, the next best thing to that is actually palm oil plantations.
No. Yeah, yes. I had to be really careful about how I worded some text related to that. It's a great point. I mean, so basically, just to make sure you caught what he's saying, basically it's like fire probability is really high in non-forested areas. It's not as high in palm oil. And there's economic incentive to plant palm oil, much more so than there is to plant forest, for example. So like all else considered, do you just put palm oil in to reduce fire? It's a really complicated issue, right? I mean, there are ecological issues at play here. There are political, cultural, social issues at play here. One thing I will say about that is that people often degrade the hydrology in order to plant oil palm. So it makes, in the long term, it makes the fire much more, or the landscape much more susceptible to fire than it otherwise would. When it's non-forested, degraded area, there's still this capacity for it to regenerate. potentially. Whereas once it's oil palm, you're putting canals in, you're degrading the hydrology, using fire to clear, or using fire to like get pests away, then it takes an alternative trajectory. Where in the short term, it might look better, but in reality, probably not. Yeah. It's a really good point, though.
I'd imagine that they're suppressing fires in these palm oil areas, probably establishing higher burn likelihood in the future after they don't have a crop there to consider.
Yeah.
There might be a hidden danger, kind of like you were saying in the long term.
Yep. It is the one group that does have the sort of money available to fight fires. So I did see, this is just anecdotal, but in some areas I would see there were these patrols, these fire patrols that were oil palm company funded, that were fighting fires in areas that were not oil palm concession owned. Which, I mean, they have like a selfish incentive to do that. They don't want those fires to escape onto their concessions, but the result is that they're actually fighting fire on the landscape, which is a positive thing. And they just have resources available to do that in the area I was, at least, the local communities don't have those resources. So there's pros and cons for sure to everything that's happening on that landscape. Any outstanding questions related to passive satellite data or any of the products?
But what is snowfall sampling?
Oh, snowball sampling.
Snowballs.
You basically talk to someone, you get an idea from them about what's going on and also who else to talk to. So it's a way of contacting additional people.
Snowball.
Yeah.
Pick up more people to interview.
How did you store all of your data?
Oh my gosh. Like not well. It was before I really learned how to organize things. I would have made like a hierarchical folder structuring and maybe a folder for intermediate products and final products, but it was honestly just a tangled like web that I went back and cleaned up. So that's another thing I would say. The more organized you can keep your data as you go, the better. And I learned that lesson in the last few years where I didn't know it when I started this project.
And then did you store organize your data?
It saves you many hours
Of work.
of frustration and confusion.
Where did you store it? Like on hard drives or in cloud?
Yeah, I just had it on like an external hard drive. But now I would put it in the cloud, now that I know how to use that stuff. Yeah. Great, thank you guys so much.